This is from Exam 2, Question 1. It's the 2000 for response question number 3. We're looking at Part C. So it says that anhydrous BeC2O4 has impurity, and we're trying to figure out how much of it is impure. And we're looking at a redox, which it gives me the balanced redox. And it tells me that it takes, for KMnO4 is used, and it takes 0.0150 molar and 17.80 milliliters to reach the equivalence point. So I can find from that moles. Now, the first question it actually wants me to do is to figure out the reducing agent. So I'm looking at this, and I've got two things that it could be. I have my MnO4 minus goes to Mn2 plus, and then I have my C2O4 2 minus goes to CO2. So I've got to figure out which one's the reducing agent. So reducing agent means it's oxidized. And if I think of Leo says Gur, lose electrons, oxidize. So I know it's going to lose electrons. And if it loses electrons, it's the reducing agent. So if I look at this, let's see. Let's figure out the charge on this, and I can figure out if it lost or gained electrons, or I could just balance it. So let's see, each O is 2 minus, that means 8 minus, this whole thing has to be 7 plus. So did it lose electrons? Well, I need to give it electrons to go from 7 plus to 2 plus. I have to give it 5 electrons. So I'm thinking this is actually the one that's reduced. But let's check and make sure when I balance it the other way. MnO4 minus goes to Mn2 plus. Clearly I need to add 4 waters, then 8 hydrogens. I look, this is 7 plus on this side, this is 2 plus. I need to add 5 electrons, same thing that I thought. That's definitely reduced. So this is the oxidizing agent, which means this is the reducing agent. Alright, so now that I've answered part 1, now let's look at part 2. It says, for the titration at the equivalence point, calculate the number of moles of each of the following that reacted. Well, I know KMnO4 at the equivalence point, so I know MnO4 minus. I'll find that first with my information given up here. So I have moles of MnO4 minus. The K is just a spectator ion, so I can ignore it. It's 0.0150 molar times converting this to liters. And take out my calculator. Let's see. 17.8 divided by 1,000. That gives me my 0.0178 times 0.015. That gives me 0.000267 moles of MnO4 minus. And if I look, I need to calculate the number of moles of the oxalate 2. And to do that, I'm going to do my T-chart because I have a balanced equation. So if I know 0.000267 moles of MnO4 minus, and then look at my balanced equation, I want to find moles of oxalate. Well, my coefficient in front of MnO4 minus is a 2. My coefficient in front of oxalate is a 5. So I'm going to take that number, multiply it by 5, and then divide it by 2. And I get 0.0000, whoops, I forgot a 0. It should be 306675, so I'll put an 8 there. Moles of oxalate. So these two things are my answer to part 2. And then it says calculate the total number of moles of oxalate that were present in the 100 milliliters of prepared solution. So I actually have to go back where it tells me how much I have. So if we look at, this is now 3C3. Well, I had 100 milliliters, and it was 0.345 grams of anhydrous BeC2O4. Let's see. Calculate the total number of moles that were present in the 100 milliliters. So, looking at this, I have grams and I need to figure out moles. Well, I know I have 1 mole of BeC2O4, and that molar mass I found before was 97 grams. And I know that I also have 1, for every BeC2O4, I have 1 mole of oxalate. So I can figure out how many moles of oxalate. But now that I'm going through this, I'm actually thinking I'm doing something wrong, because this tells me that there's an impurity in this. So this is how much oxalate I'm supposed to have. But I can't actually use that because I don't know how much of it is the sample, this 0.45 grams, is really this. So I'm actually going to stop and I'm going to say, wait, part 3 must have to do with part 2. Because I found out how many moles, I found out that I had 0.000668 moles of oxalate. And if I go back, it says I figured that out from 20 milliliters portion of this 100 milliliters. So that must mean if I take 5 times as many, I have my 100 milliliters that I want to get. So I must just have to multiply this by 5. See, and this is the hard part with AP problems. Sometimes you make them way more complicated than they need to be, and you got to go back and check. So when I do that, I get 0.00334 when I round moles of oxalate in the 100 milliliters. I'm glad I caught that before I did all the stoichiometry for it. So to go back, the reason why I couldn't do the stoichiometry is part of this 0.345 grams is not pure. So if I assume it's pure, yeah, I could figure out how much I was supposed to have, but I want to know from my titration how much I actually have in there. Now when it wants me to calculate the mass percent of BeC2O4 solid in the impure sample. So if I know I have this many moles, let's calculate how many grams of BeC2O4 I have. Now I'm going to use my stoichiometry. So I have 0.00334 moles of C2O4 2 minus. I know I have 1 mole of that for every 1 mole of BeC2O4. And now I know the molar mass is 97 grams. So when I multiply that by 97, I get 0.324 grams, and that was out of my 0.345. So now I'm over here in my little corner. I'm going to do 0.324 divided by 0.345 times 100. Let's see what we get. That's 93.8%. So 93.8% is my answer to part 4, and this many moles is my answer to part 3. Oops, and you can't really see my answer, so I'll move it. Sorry about that.